Good afternoon, guys. We're talking about photon mapping today. This talk's inspired by a project I worked on about 10 years ago called My Virtual Home, and I was tasked with doing the lighting, and the lighting had a few interesting requirements. Because the project was designed to actually sell buildings and building materials, including wallpaper and carpet and furniture, the lighting had to look realistic. It was supposed to be as photorealistic as possible. And we needed to produce a runtime result that ran on GeForce 2-level hardware, and the process needed to run about 64 megabytes of RAM. So it's a little bit of a tall order for today, but in the past I've done some radiosity-based light mapping type things for some different companies and different projects since about the Quake 2 era. So I had a go at this before. It was, anything visual, as you know, as programmers, visual stuff's fun because you see something on screen and it's quite exciting. But although it might be a bit historic, and certainly what I'm doing here, I wouldn't say there's a huge amount of need to do things as it is today. There may be a reason you might want to have a go at it. There may be a reason. The My Virtual Home project is really, I suppose you could describe it as AutoCAD for grandma. So it's a kind of program where you can, I'll show you a screen just later on, you can drag a mouse and drop a kitchen and drop a building and resize the walls, drop some furniture in, select the floor and just say change the carpet and see some results. So it's really designed for customers who didn't know about computers.
Used to give it away on magazines and stuff, didn't they?
Yes, they did, like the Home and Garden or something like that.
Cross promotion,
So the problem we started having with visual applications was that in order to achieve more realistic lighting, we had increasingly complex lighting models. We started off with maybe dot product, and that was probably stored in a table for speed at the time, and went into all sorts of, we can see a bit of bi-directional reference, something or other, a bit of, I forget what it's called, Fresnel, something or other, I don't know, but anyway, pretty crazy stuff which was hard to understand, and what it really was trying to make mathematical models of real light. When in reality, a lot of complex models are really approximations of continuous, simple functions. You can imagine dropping a ball and having it continuous under gravity. As a programmer, adding a little acceleration is quite simple, but then you model that over time and it can become more complex. So what is photon mapping? What we really do is we simulate light, and we simulate it at the most basic and simple level possible. It really isn't a whole lot more complex than what you saw on the first page of an emitter, emitting light, and those photons being treated as little particles which are fired and they bounce off surfaces. So the process works something like we collect our light sources in a scene. This is very heavily, I have to emphasise the point that we make heavy use of random numbers, and we make heavy use of statistical relationships. So if we had a room with two lights, where one light was twice as bright in energy terms as another, if we were firing photons out of those lights, we would fire twice as many photons from the brighter light than the dimmer light. Okay? In our case, all the light, each photon we emit is at the same power. When we go to hit a surface, we cast a ray out into the scene. I was using polygon scenes. You cast a ray out, you find a surface, and then based upon its properties, if it was diffuse, we would generate a random number, and based upon its level of diffuse reflectance, we would either store the photon at the surface, or we'd reflect it, or we can do both. Okay?
Stored, the surface was lit, was it, or something like that?
Kind of. So just think of it for now as storing. We'll get rid of that.
Hold it for later.
Yeah. When it is reflected, though, we allow the energy to drop, and we also allow it to be filtered. A white photon hitting a green surface is going to reflect the green. It's going to leave the remaining colour at the surface. or the random energy at the surface.
Extra photons with each of those, or just the same one?
It will effectively split into two, so one photon fired could become two in the scene or more.
Okay.
Yeah. And you can think about it, there's actually an early bugger I remember having. You don't need to have things like cosine and dot products per surface. You imagine if you have a surface like this, okay, and think of it as it turns through that. If you had light travelling directly down and it hits a surface like that, okay, we have a lot of light coming down. 100% of the light is going to hit that surface. It's travelling parallel, it's going straight and hits the surface. Imagine if the surface is now like that. 100% misses, there's no light. Okay, and you think of it from your cosine rules, your dot product there, of that. If the surface was like that, if you find about 70% of the light hits the surface and about 30% misses, and it's really just due to the geometric orientation of the surface versus the light. Okay. Now, when you simulate photons, you don't have to bother with even something like the angle of the surface versus the incoming direction of the light. It's purely geometric. It's just like basketballs flying around boards, nothing more. All the values come out in the wash, so to speak. You know, it's a bit like saying you've seen people before who do experiments on YouTube. They drop a bunch of nails on the floor, and then they measure pi, or they measure cosines, or they measure distribution, they measure functions just by counting how many fell in different ranges. You know, things like that. You know, so we're just doing a simple physical simulation here.
You basically get less photons hitting the surface, same with more parallel to the direction of
That's right.
Yeah.
Yeah. So it's that simple. Okay. So when these photons are collected, we store them, and if we were to look at what they look like as just points of light stored in the scene, you get something like that. So on the left there, let's see if there's a less squeaky seat so I can sort it down. The scene on the left there is actually my test scene. I add and take walls to it, add and take balls. That's a little table there, and he actually has a texture on him, of which some of the texels are transparent, and so you can see some of the light has gone through the smiling face of the floor. The other scene over there is a kitchen, part of my common test scene, which was a real, fairly complex model of a house. That scene there has, the scene here has one light that's above the table, it's invisible, it's above the table and points down. And that scene over there has two lights. One's a ceiling light, and the other one is actually a wall lamp, which sort of lights up towards the ceiling, I believe. Okay, so when you have a collection of points, and if you did this naively, you'd have a bunch of x, y, z's in space, a great big array of x, y, z's, and maybe some energy value. Okay, you have to try and do something with it. How can I make use of this? Something that people do in photo mapping, if you read the old literature, is they sample it. So they grab a bunch of photons, and pretty simply here we're dividing the number of photons by the area to try and find the density. If you were to use that kind of average energy level and plot it as a texture, you get something a little bit like that in the corner there, which kind of looks nice. Looks a bit nice. But there's some serious problems with it. You can probably tell that the walls look pretty motley, pretty uneven, they're very blotchy. That's because the process was driven by random numbers, and just like we saw here, if you ran this for hours and hours, you'd end up with a scene that's almost pixel perfect as we simulate billions and trillions of real light particles. In fact, I think just now, when I googled some months ago, there's actually photon mapping, like ray tracing software, which does this, and you can just sit there and watch the image get better and better quality over time. It looks quite nice.
It's not good enough, probably should.
Yeah, very slow process doing that. So yeah, we get this blotchiness, and that's due to random numbers. Okay. Then you can see the corners look a little bit too dark, and they are too dark. And the main reason is this right here. We've hit an edge, and on that edge we've sampled what we believe is we've naively sampled a large space, but actually collected very few photons and so we biased it and it's too dark. And you might think, well, that's we'll just correct for that. Well, that's actually really difficult. It's not technically difficult. You can imagine if we had that geometry, we could, for instance, forget these being circles for a moment, let's do them as rectangles. Rectangles work just as well. Why don't we clip the geometric rectangle to the polygons? We can use a polygon clipping routine, actually measure the area. That's fine, that works. It just happens to be so slow in practice that the system uses a lot of memory and goes from what I'll tell you is very fast to being incredibly slow. So it's not practical. I certainly be considered. By the time I was doing this here, which was only fairly early on in the research project here, I was getting a bit disillusioned by this time, a bit disappointed, and realising that this is what people were producing on the right-hand side, and they weren't getting much further than that. And I'll tell you why. I'll tell you why after describing how we put those dots into something useful. We do that. Can you actually read that back there? Okay. The data structure of choice for this type of exercise is the KD tree, and the reason is that the KD tree is stored as an array. Because of that, the position within the array represents the parentage or the linkage as the structure of the tree. So we don't need to have nice big fat pointers pointing to parents or children, child nodes. That's the main reason. So it's really just a tight data structure. It represents a binary tree. And what we were finding in the research is people were using balanced KD trees to work with their data. And this actually turned out to be really, really useful, far more. Nothing invented here. A lot of people did it in different ways. Some people did it naively, just with your typical tree structure. You get a structure with two child nodes, and maybe a value for X, Y, Z for where the splitting plane is. Okay. Now I'll tell you a few things about it. If you look at the top, that's a valid KD tree, but it's unbalanced. So we have the same set of dots, and I purposely biased it to be an all right-hand side, and you can see the resulting tree. There's nothing wrong with that. It's just a valid tree, but it's not particularly useful. If you balance it perfectly, you get something in the middle there. Now, I also found that some people try to dynamize these things. I didn't actually use the dynamic tree really for this project, but I made a dynamic structure later and just used as a general purpose n-dimensional data structure, which is useful from time to time. And the way you do that is you have your static tree, and you append, as you add nodes to it, you append them to the end. And you can also flag nodes as deleted, so you can delete nodes and add nodes. And when you increase the tree size by, say, 10% or some factor you've determined, you rebalance the tree. So you just delay the work. Now, how do you actually create the tree? It's basically like a quick sort, or more precisely a half sort. So I don't know how familiar you are with those sort of algorithms, but they're actually fairly simple. If you have an array of unsorted data, you find the middle, you find the median. You don't actually care about the order. What's important is half have to be greater and half have to be smaller. You find the middle, and you repeat that process, the middle, the middle, the middle, and by the time you've done that, the whole thing is sorted. So the process is fairly fast, and that's all this is. So in each of 3 dimensions, you find the middle, you sort the half. With STL, you can do that in a few function calls. I think there's even a half sort as part of the algorithm skip there.
So what are you storing in your nodes?
We're storing, the XYZ position, I believe, and we are storing the energy amount. And the energy amount is compressed because we're trying to fit this. Remember, this is early 2000s. Memory is pretty precious. We don't have a lot of space for big floating point numbers. I think I was storing it as I have to look at the paper, but I believe it's something like 1 or 2. It's something about the nature of 16 bits for colour and 1 byte for an exponent, or something like that. So it compresses and decompresses into a floating point RGB of a fairly high range.
So is it effectively a voxel?
The tree itself represents voxels,
Yeah,
absolutely.
okay.
Yes. So you could say it's a bit like an octree or a voxel
Yeah.
tree. You're splitting on planes. Rather than having 8 children, it's a binary tree. So it requires, you can imagine if it doesn't require division in each dimension. You can go XXX.
But you're storing the 3D location in each node, so you don't need to.
That's right, you don't need to derive that. What I do though, you have the X, Y, Z, I do actually store 3 bits worth, which say which of those values represents a plane. So yeah, one bit set, X plane is going to be the splitter here.
Okay.
So if that's of use. Okay, so what I'm trying to say here is previous researchers used the KD tree to save memory, so they can store photons. Because they want to store them in the millions range, typically the millions, not much more than that, but we're talking about computers with megabytes of RAM back then. Hundreds of megabytes was a lot of memory. And I'm suggesting that there's particular value in the balance tree, and I'll tell you why. And also, just as a point, you can dynamize it and make it as a general purpose structure, and you can use it as a map, a 3D or an n-dimensional hash table, which is convenient if you're working with geometry. If you're writing tools for maybe mesh processors.
Navigation companies. Navigation companies.
Oh, yeah. Not in my case, but yes, those sorts of tools, absolutely. Now, nothing I've done here is revolutionary. It's just using what other people have done, maybe in a slightly different way. And I noticed one research was saying when you balance the KD tree, you have a perfect distribution. If you grab the top levels of the tree, you actually have a representation of the levels below it. And that makes sense. If you've done voxels, we saw last week electron voxels, if you grab the root voxels, they're a very coarse approximation of the voxels beneath it. In fact, many compression techniques use that. You see octree compression, that sort of thing. So it should be a no-brainer, but it took some time to click for me. Hey, what about the top levels? What if we put a few million photons into a seam, balance sorted it, and then just grabbed the top arbitrary number, top 1,000? If you did, you'd see that. So those little red dots represent the top 1,000 of 1 million points of light. And they happen to be collected around the light sources and where the first reflectance is. So it's hard to tell because we're looking directly down at the scene here, but a lot of those red dots are on the ceiling, reflected, and on the floor, reflected as light coming indirectly from the light sources. Okay. Now, the thought was, what if we use those lights, those photons? What if we could sample the energy at those points and turn them into indirect lights? Okay. So recall this. If we go back, that's sampling, and if we directly visualize the sample, we get that motley, blotchy, error-prone scene. But what if we use the KD tree and we balance it, then we just grab the top arbitrary number, and then we do the sample. We actually grab each of those points in space. We sample out from them to collect an even number of photons. We find what is the light concentration at that point. And then we just shove them back into a direct lighting system, a normal conventional renderer, and render them as if they were normal lights with a light source. Why should they even work? Well, there's a good reason it should work. Very good way to roll my mouse from here. And that is the way ray tracers work. Now, a classic ray tracer, don't know how familiar you are with it, but I'll describe it in a sentence or two if I can. You fire away through the pixel of the screen, you hit the scene, you don't end there. You actually then fire rays back at the light sources to see if the light sources are occluded or not. Okay, that's the most basic of ray tracers. Now, the ones you see on TV and movies that actually do, everything from Toy Story in the old day to Final Fantasy and Pirates of the Caribbean or whatever, rendering movies, they do an awful lot more than that because they want to capture more of the light. They do what's called the final gather. And the final gather, if unaccelerated, would mean when you get the surface point, you actually cast out thousands of rays. and you might even reflect them around the scene. So they could spawn thousands upon thousands of rays to try and get some indirect lighting in the scene. Now, a way to accelerate the final gather to only be a few ray casts is to produce what you saw before, well, that thing there, and store it roughly as textures. And when you do the ray trace, sample those textures, because those textures represent the ambient light in the scene. So those ray traces don't directly visualise the photon map at all, they simply use it as a phase of sampling, and they can accelerate that final gather to make it practical, to not take days for a frame, but take only minutes to hours for a frame, but still have that ambient lighting that we crave. Okay? So that's what the professional guys do. What I'm trying to do is create the final bounce. So I'm analysing the scene and trying to create a light which represents the final bounce of light to the surface. Okay? Energy is completely conserved in the scene. The energy that was emitted is either absorbed or reflected around to eventually be absorbed across the whole scene. We pick an arbitrary number of lights, 100, 1,000, 10,000, whatever we want, from a scene of photons, hundreds, thousands, millions, billions. Just grab an arbitrary number, divide our energy up, use our sampling, and then we can create these lights. Okay. So we create these lights and we get what's seen on the left. Looks wonderful, except it's got acne. It's too bright. So we have a bit of a problem there, and we're at a stage now where I have to admit some of the inspiration for direct lights was a paper from the 90s called Instant Radiosity, where a guy was using some method, I guess it was some radiosity type method, to calculate indirect lights and use lots of lights to create an ambient lighting. So that was some inspiration there. So this is really me taking the photon map and the KD tree and making those indirect lights. And he encountered that problem too. It turns out there's actually a fairly simple way to do it, to solve it, and that is you can bias the lighting function. You see, the lighting function for radiation is roughly 1 over r squared, 1 over distance squared away from the light. You fall off, exponential fall off. Ignore the pi for the moment, but the pi has some significance later on. In this case, by simply modifying the function a bit, we can clip it off. Instead of approaching infinity as we get closer to the infinitesimally small light source, we can clip it off at something arbitrary, and we can just lose that peak. So it actually turned out to be a very simple and easy fix to make lots of lights not be super bright right where they are. And that's pretty much the final quality we're after. But there's more problems encountered in this scene. One is that the whole surface, so the whole process is still slow. When you cast rays around the scene, particularly in my case, I'm lighting texels, and in our case, the texels were somewhere between about, well, for a coarse approximation, 1 texel per metre. For a final quality, 1 centimetre per texel. Maybe something in between for a lower quality. When you start doing that, you have millions upon millions of rays, and you need to accelerate it. So I used a variation of the binary tree, a variation of the BSP tree. A BSP tree is a little bit like the KD tree we talked about before. Space is just divided up using planar splits, and I investigated a whole bunch of different things to try and speed it up, and found what worked best for me, the kind of geometry I was working with. Because I had scenes where there were very large areas. We had entire buildings, multiple stories high, multiple rooms wide. They may have been tens of metres in total. But also we had things like this here, and that was about a 30 to 60,000 polygon coffee machine or drink machine there. And they obviously, we even had, I think there's a pot plant made of about 10,000 polygons for just the flowers. So it had very tiny details, a lot of density in polygons. We need the process to run fast. I'll have to get back to another important factor of the photon map later on. In this case, the BSP tree used axis-aligned splits in the top levels, so basically it's voxels at the top, and when you got down to a certain size, there's a certain threshold that was met. It wasn't arbitrary, it was calibrated. It was going to planar. It would actually use the polygon's own planes to do the splitting after that point. And I learned an awful lot about the behaviour and speed of tracing BSP structures, and I found that most of the literature on the web was false. For instance, a lot of guys were saying, if you balance the tree, you can take up less space and cause better traversal. That's complete fiction. What you want is a tree that requires that when you trace it, touches the fewest possible nodes. And touching the fewest possible nodes has got nothing to do with balancing it and so forth. In fact, sometimes you want an almost completely unbalanced tree to get the best performance, because what you want to do is cull. Every time you hit a plane, you want to eliminate as much as possible, not divide work as evenly as possible. Polygons were stored in the leaves, and not even as polygons. In the end, I saw them as derivatives of edges. The idea was to eliminate all divisions, and I could actually do a pointing polygon test in just a few multiplies and adds. So two-dimensional, they were projected, each polygon was projected onto its axis, so it was actually two-dimensional edge structures. And even then, I pre-sorted them. If you had a long, skinny polygon, I tried to pre-sort the order of the edges to get early outs. So that's the sort of effort I went to try and make this a fast structure. And the end result was pretty good. With all techniques together, which was top-level culling, BSP runs, some caching and so forth, I managed to achieve 2 million raycasts per second on Pentium 4. So just very quickly going back to the Photon map, I'll try and get back to just to show you the Photon map. I'm storing photons without the geometry, right? So firing rays around the scene, bouncing off the polygons, just raycast versus polygons in my case. You can do this versus voxels or versus curved surfaces or whatever you like. When we get this point, it's just an X, Y, Z energy, okay? Everything else is thrown out, so you actually don't need the geometry after that point to create the photon map. What you do with it after that. So if you had this problem here, it's not easy to correct because you don't even have the geometry anymore, okay? Sort of make that point. Okay. Fairly simple problem here. When you do have a bunch of textures that represent surfaces, how are you going to store them? And I've done nothing special here, so I'll only mention it briefly. Imagine if you have a sphere, if your model is a sphere. I used a simple unwrapping method. I did axis projection, so a sphere ends up being mapped to roughly six axes. So all those neighbouring polygons get stored together. And then they get bounded by a rectangle. I can allocate some texture pages, which are just rectangles, and insert the boxes largest to smallest, and that packs them, with reasonable efficiency into a page. I do one or two other things. One of them is that because you can see that huge rectangle there with bigger empty space, that's like a whole room. At this resolution, the whole room can be projected into a single texture, but that represents the walls on the outside or something like that. So there's a big hole in the middle. We can determine that is in fact empty space, it's not used space, and I can just reclaim it. So I actually reclaim boxes within the middle, and I can store geometry inside there. Okay? So there's nothing really...
Is this for storing the photon map?
No, this is for storing textures. Sorry.
Just normal textures?
Yes. So in my case, I'm not ray tracing the world to create a render. I'm ray tracing to the surfaces as texels, and those texels can be from about 1 centimetre to a metre in size. And so you're going to store them as a bunch of texture maps to do, just apply them as a separate pass or a multi-texture on a GeForce 2 level machine.
Does it actually include the diffuse texture that was on the surface in the first place, or is it just the energy level that's stored?
This is just the lighting, so it has the light and the colour, but not the diffuse map, you're right, that gets applied separately. And the original may be tiled too, like if they have a piece of carpet or brick wall, that may be tiled. This is unique. One other optimisation is if the page is half full, I just, less than half full, I halve the size of the texture and send it through so I could make smaller pages, but that was just to save the memory. Now, there's nothing special about this, and I don't even recommend doing it these days. This is part of what's called the texture atlas problem, and it becomes more pronounced with this. When you do map textures to different surfaces, curved surfaces, it's only runs to curved surfaces, you encounter the map maker's problem, and that's simply mapping a curved surface or a round object to a flat plane. Now, I spent quite a bit of time trying to eliminate seams, this artifact called seams, and I could never eliminate it completely. I did get some improvements with some filtering effort and certainly alignment of texels. You can see from here, those are actually texels. That's a low resolution map, and those are individual texels. And you can see that over the curved surface, they actually line up and meet across the different planes. They actually meet perfectly. So that took a bit of effort to do, and it turns out that it didn't help because it's actually bilinear filtering that kills you. And even if you have the texels themselves lining up perfectly, once the bilinear filtering draws in its neighbours, you'll start to get discontinuity of colour. And you'll see, if you can see the bottom right there, and certainly the other one, the top right as well, but that's basically a low and high resolution of similar scenes there. You will see seams. Now, what the researchers have been doing is using mathematical models which try to reduce the, what was it? They use a balancing function which tries to put a cost associated with things like warping and unwrap. So they have like a model of a cow, and they unwrap the cow into a single skin, like a hide, really, I guess. And they do other things like split the seams. Obviously, if a cow's going to unwrap itself, it's going to crack. They split the seams like on the underside of the cow along the insides of the legs. And they use things like, if you were to view the model from the outside, you're less likely to see the seams if they're in places that are hard to see. So there's some really good texture atlas and unwrapping methods these days. 3ds Max has some great unwrapping tools. You can buy them, you can get them as free. DirectX, I think, has a DirectX tool, an unwrapping tool. And when you have an unwrapping tool, you can often generate UV coordinates from it. So with an atlas, you don't even need to do some of the stuff you just saw there, like that. Because what I did in the end was actually generate the atlas first, and then map the atlas back to the scene. So I'm rendering basically onto the texture, and that's how you programs like 3ds Max work as well. You generate your atlas and then you work back. And the main reason I did that was not so much because it's just a nice idea, but because if you work backwards like that, you don't have to saw the whole scene. You can actually render one texture page at a time, and you don't have to store all of the... and as you do one texture, you can toss that in memory. So what's in memory at any point in time is very little. And I do know that there's no perfect solution, because every few years you get a new paper come out which says, we've solved the scene problem. And every year it produces a wonderful result and doesn't solve the scene problem. But there's some lovely ones. I believe it was Disney, but I'm not sure. They don't even do some of this. They actually put every single triangle is its own unique texture. And they put a fairly high texture map on it, and I believe they use a bunch of boundary texels, and that helps the filtering across the edges to almost eliminate those seams. So it uses a lot of texture memory, but hey, memory's cheap now.
Is that the P-text thing that came out?
I think so.
That would have been busy.
Yeah. So it's some nice results, but it's not a there's no ultimate solution. You're still trying to map a round surface onto a rectangular plane. Another problem I encountered, what appears to be light bleeding at the edges, and it's really to do with feature size. If you have a texel that is 1 metre in size, and your wall is paper thin, then what are you going to colour that texel, right? Whereas if you have a texel that's only 1 centimetre in size, and you have a room which is made of pillars that are nice and large, you really only have little issues like this. So I'm trying to get you to visualise the problem here. The size of the texel versus the size of the geometry affects how you should colour the texel. And what we're really saying here is that these texels here represent little places on the floor, under a box or a pillar here. Those ones there are correctly in shadow. Those ones that are in error, they're showing the inside of the box. And it actually turns out to be fairly simple to solve that. You push the sample point around. Instead of sampling in the centre of the texel, or having all the points scattered around the texel if you're doing multi-sampling, shift it out. So And that actually turns out to be fairly easy in the polygon world as well. And the idea is if you can see a back face, or see lots of back faces, you're probably inside the model. I purposely work with polygon soups because polygon soups allow artists to produce junk. And I love artists, but they produce a lot of junk sometimes. And what I mean by that is that they will produce, if they put a pillar on the floor, they will quite reasonably quickly whip up a cylinder or something and quickly whip up a plane, and they won't care whether it's floating slightly above the floor or fully embedded in the floor. And why should they? That's a waste of their time. Okay? So I, as a tool writer, should be detecting and correcting that. And back in the Quake days, you might have tried clipping it. And clip the polygons together, throw out the ones that were in between, maybe even try to use some other structures to seal up gaps. But if you can algorithmically, most of the time, clean up junk, then garbage can come in and a reasonable good result can come out, and that makes everyone happy. So in this case, yeah, if there's junk geometry, big deal, and there's junk geometry everywhere in my scenes. If the texels are too big compared to the scene like that, and this is going to be noticeable, just detect if that sample point, in my case, I fire a tiny ray. The ray only has to be about the size of the texel, so if your ray might be a centimetre long or two. When you fire rays that small, you can cull an awful lot of the scene before you actually have to test any geometry. Those tests tend out to be very fast. Okay. Shift the sample points and yeah, we set your sample on the outside of the geometry.
So when you're doing your checking to see if you're inside some geometry, you cast out another, 6 rays in arbitrary directions and see if you...
Pretty much, yes. So exactly that.
That's not expensive for each texel?
Doesn't turn out to be.
Okay.
No. We can detect due to some method whether we are near geometry. So the data structures I was using, I used a surface structure which had it wasn't a winged edge structure, but it's a structure which determined whether it was near neighbours. So I can immediately say, you've got geometry intersecting you or not. And then we can do early outs all along the way. So very few texels did ray casts, and when they finally did, they were so short, they were incredibly fast. They turned out to not be a bottleneck.
When you discovered you're inside something, which direction did you move the photon?
Yes, so I think I had, this is from memory and it's all in the paper there somewhere, I believe. Basically corners, I think I had a little list that said try the centre, then try the 4 corners, then try in between the 4 corners. So I had a preset list, and it would, in its worst case, would go through those 9 or 12 points or so, giving it a go.
You would do the 6 directions or whatever.
Yeah, so
on each extra section.
Yeah, because if you do cast one ray and you hit one back face, you're not really sure because there's junk. But if you cast a few rays and you get mostly back faces, you're almost guaranteed to be inside geometry.
Yeah, and you have to limit what you cast in those rays against to protect your back faces too.
Yeah, remember all we're trying to determine is whether one little cube of that size is in or out. And if we can move it out, we're happy. That's all we're trying to do. And the results were pretty good there.
I've just gone back and abused my artists and gone to
Yes, well, too much of that happened back in the day. It's not fair. Yeah, artists should be creating wonderful things, not doing technical fixes to scenes, really. So this is what happens when you make lots of lights, well, a few lights, but the lights are heavily occluded. So the reason we have those sort of harsh, sharp edges is because they're shadows. The light is actually inside. Most of the lights are inside the lamp, and they're being occluded by the lamp cover. And there's not enough samples, so it looks pretty ugly. And you can think of that as being a little bit similar to when you've got a football stadium of lights, and they're shining on the soccer player or the cricket players, and you see maybe 6 or 8 distinct shadows coming off them. They're not getting a nice softness there. What we'd like to see is something a bit more like that. And this scene is interesting because that's a single spotlight. There is one spotlight above the table. That's not a light, that's a table. The light's above the table looking down. It is a spotlight, and it's producing a soft shadow. And I've got a quote for this. We have Hassan Fratz, who said that soft shadows are a consequence of partial visibility of an extended light source. So basically saying the light is big and it's somewhat occluded, which creates a soft shadow. And he's right. So all of the lights in this simulation are actually surface lights. If you give me a light bulb, I'll take the energy reading, the 60 watts or whatever the rating of the light bulb, and I won't put a point in the scene, I'll make a little sphere. And when I cast rays, photons from that sphere, I'm going to fire them off in random directions based upon the surface of the sphere. We're going to have a spotlight. Once again, it'll be from a circular type shape, limited by the arc of the spotlight. And area lights too. If there's a window with the sun coming in, we'll get the time of day and the time of year. We'll do that. The size of the window, the tint of the glass if need be, and we will emit across a jittered grid of that whole surface to have sunlight coming in the window, and then those sample points will become photons. So now that we've done that, we end up with some nice looking light, but sometimes it's too bright or too dark. And we have the typical problem with a camera. If you point at the sun, or how the difference between a dark room and broad sunlight is millions of times difference. It's dramatically different. So you need to calibrate it. There's actually the function there, brightness equals 1 minus E something or other. And this is a standard exposure correction function. We can plug in different constant values and we can correct for exposure really. And we can see that's just putting in for fun a value of 0.5, that's a value of 1 or none, that's a no exposure, and that's a value of 2. You can sort of see the dramatic difference you get there. Really changes the shape of the apparent spot or the dot of the light there, or the intensities. So that can be calibrated. I don't know how it was done in our project. I actually created a little SDK where you just fed it to, it's like begin polygon, begin model, add light, just simple feeding. It's like OpenGL. You just feed it some geometry and lights, and then out comes some textures. But you can calibrate it in different ways. The way it's often done in games these days is you analyse the whole scene, or you analyse the whole frame, and you add up the total light, and you say let's dim it down so we reach a threshold which is not too bright for the user. Okay. Now remember those lights way back at the start. I said there's a pi in there, but don't pay attention to it. Okay. So instead of light decaying at 1 over r squared, to actually light all those indirect lights were not just simple lights. I said that the lights were stored on the surface, and they actually, I said we took the KD tree, we took the top level, we created lights, we sampled, and we said how much energy should this light emit? Okay, we used that area as an actual density type of area estimate. And we use the size of the texels, you saw those little blocks before, we were shifting the sample points, the actual size of the texel as a receiver. So the light becomes an area light, and the receiver becomes an area receiver. When you have area to area, we can do an area to area energy transfer. And how do we do that? We grab radiosity techniques, and we look at the form factor. The form factor of radiosity, there's the function there in lovely maths. But if you want to visualise that, that's a reasonable way to do it. Imagine that your eyeball is a texel. You're looking up through the texel in the floor, and light is coming in. It's actually indirect light from all over the world. It's coming in. When light comes in from another part of the world, it's as if there's a hemisphere over the top of you. Light comes in through that hemisphere, hits your eye. It's projected down onto the disc, flat onto the disc's surface. That is the amount of energy you receive from that area out in space that you can see. So that's the energy from one area to another, and that actually produces a beautiful lighting result. Okay, it is based upon the form factor from the radiosity method. And here we get to some final results. So if you actually render a scene, and that scene there may have taken an hour and a half or so, that's the kind of quality you get. So I was fairly pleased with that back in the early 2000s. And I think it probably still looks fairly nice. That's a pretty good looking dunny. You can see soft shadows, light bleeding underneath the couch and table and so forth there. We've got a ceiling light, one ceiling light in that toilet produces all that effect. Just from a different view, you can see underneath the table there some of the distinct hard-edge shadows, some of the softer shadows. Okay, now how fast was this process? If we look at the total time, there's our total time. Total process times along the middle here. So I'm not showing you the pictures. If you grab the document this is based upon, there's slides that shows you all the samples. But basically we have the same scene, and I've calibrated different ways. I've said, what if we just used 100 lights? What if we used 10,000 lights? What if we used just a few thousand photons? What if we used millions of photons? What if we used a low-res texture map? What if we used high-res? So just those sort of playing values, different samples. So you see that it took 2 minutes to process the scene there. It took 10 hours to process the scene there, and then we have other ones in between. And what we find is that test 6, which took 24 minutes, actually produces the same, not the same quality and resolution, but the same representation of light as the 10-hour process. What that means is, because we've calculated the energy correctly, we can fairly rapidly produce a result that the user can say, that's what the light will look like. Okay? And still, in the lowest one, 2 minutes, we produced a result. It's not quite accurate, but at least it's a result. And the reason is this application, as it's running, the user's dragging walls and dropping couches and changing carpet. And if they leave a room for 2 minutes, up pops some lighting to show what the room looks like. And after a little while longer, it looks better. And if they leave it, or they hit like render, if they leave it for a while and hit render, they get the final quality lighting. Okay? And if they move something, depending on how much they move, it'll either use the light maps or it'll just toss them out and start again. Okay, but I have some red arrows here to point out some interesting timings there. So although we have 10 hours and 40 minutes and 2 minutes and 20 minutes there, building the photon map took 2 seconds, 20 seconds, 40 seconds. Okay, it wasn't a particularly slow process. Balancing the KD tree took 150 milliseconds, 1.7 seconds, 3.8 seconds. So for 1 million or so points, sample points, we didn't spend a lot of time there. Creating the indirect lights, that's really just grabbing those sample points, doing some sampling, doing some evaluation there. 100 milliseconds, 1 second, 2 seconds. Not spending a lot of time. Okay, which leads us to this conjecture. Why not do this in real time? We now can do deferred lighting and shading. We can render the scene into a Z buffer, we can have normals per surface, we can have our scene geometrically represented in screen space. We can put lights, we can light the world in screen space very efficiently with shaders. What about shadowing? Well, that is a problem, but it may not be a problem. And it actually relates to feature size once again. If you have large lights and small features, if you have a big light beside a thin wall, it may bleed through. But if you have small lights, very small dim lights, but lots of them, it doesn't matter if a few bleed through. Because in general, you're going to have dark where it's dark and light where it's light. And what we're trying to achieve here is ambient lighting. We're after that lovely diffused ambient effect. Okay? It still contributes a lot of energy to the scene, but it's not as dominating as the direct lights. We just want that softness. So we don't actually necessarily need the occlusion. I've actually read someone else who did light a scene with a lot of indirect lights, and they said it turned out the turning off occlusion looked better. I can't give you the quote for that, unfortunately, but other people who are working on this, you don't necessarily need the occlusion per light because that becomes expensive. We're saying the photon map creation, from generating the photon map through to having a light, a point in space with some energy to emit, only takes seconds to tens of seconds. Maybe nowadays, with fast computers, we could optimise just that process down more. I didn't optimise it because it was such a small part of my process, it wasn't really worth optimising. It was already okay. Back in those days, we had a single core. We're moving on to dual core. Nowadays, we have lots of cores. So with background processing, if the scene is relatively static or moves periodically, if the sun changes time of day slowly or the furniture moves occasionally, why not let there be latency but reconfigure the scene periodically? Also, remember I said that when the photons were stored, they were stored without geometry. They also don't need to be sampled with final geometry. So if you have a low-level polygon scene, or if you're doing voxels, you can grab the top levels of your voxel. You don't need to have the entire final quality. You can light the scene, get that statistical distribution of energy without the full quality of geometry.
Sorry.
Okay, so I think it's quite plausible to create your indirect lights in real time and then render them in real time using a deferred shading technique. This is what the My Virtual Home project looked like, just for your own interest. That's actually like the main edit screen. You grab hold of those little rectangular points and drag them around. It didn't look that nice when I was working on the project many years ago. As you hover over a table, it would highlight. You'd actually have a glow effect around it. You could just drag it around. You could actually drag the chairs under the table. It would collide with them and things like that. Okay. This is exactly what it was designed for. What if we change the colour of the kitchen? What if we tried a different floor? And you can see immediately the result. It changes the effect of light. It changes the, all sorts of stuff there. You can get an idea of what your house will look like before you build it or before you spend on that material. Here's just a few other screenshots from it. You can see some light coming through a doorway there, and inside a room there. Now, mind you, there's some lovely reflections. The reflections have nothing to do with it. That's just plain reflections. Normal texture mapping. So we combined the light map with it, and then did some other specular effects on top. Okay. So yeah, a nice looking set of furniture up there. That's a final quality and the final product in action.
It's like a high resolution light map you got on the lounge.
Yes, I believe that is. I believe most of these here are final quality. What you configure it or run it for some time. Yeah. But of course, once they're ready to texture in that day, GeForce 2-level hardware also maybe have a little bit more for both performance and a few extra features of lighting and reflection. You can move around this in full real-time, interactive rates and enjoy it. Do camera fly-throughs or just navigate it. And that is all. This information for today's talk actually came from this paper. I have to thank Greg Lane probably, because when I described this to him, I said I finally figured out a way to use this photo mapping to light your virtual homes, and he said you should write a paper on it. So I said, yeah, maybe. And I said, can I have a bit of work time to do that? And he said yes. So I wrote it up, and the document isn't really how to do all this step by step, because really how to make a KD tree, how to do general photo mapping, you can Google that and you can look up the original people who did that. This is really the problems I encountered while trying to implement it, take it from theory to something in some software, and how I fix those problems. So that's what it is. There's no exercises left to the reader really. It's more of what I encountered and how I tried to work around it. And you can find it on sites here. You can also find it on the GM Script, which is a forum that I maintain a bit. And that is all. So any questions? I haven't actually covered all that I prepared, but I think you've got a bit of a snapshot of what this is about.
So you're suggesting we could have really beautiful lighting without too much effort?
Yes, yes. I noticed at the time too, and certainly in this paper I noted in the future talk, just after I finished this project I watched Final Fantasy The Spirit Within, and after that I actually read of some of the graphic artists who created that movie, and they said we spent a lot of time placing ambient lights. We said we placed thousands of indirect lights in our scene by hand to create the beautiful ambient and diffuse lighting of the scenes. And I thought, well, even if you didn't implement this, you could have used a KD tree and a photon map to create an automatic light placer. Yeah, at the very least you've got a placing tool.
Take that load off the artist, they can focus on what they do better.
Exactly. So there's a few nuggets there, and certainly dynamising your KD tree is just another tool in your toolkit, because every geometry programmer has a toolkit of algorithms to use. Yeah.
You said that the lights have constant energy. Does that have a problem if the lights are really far away from a wall? If there's no attenuation?
Yeah, let me explain that, because I actually did not really go over everything as I should have. So if there's a bright light and a dim light, you're going to emit more photons from the bright one, right? Now, if emit all the photons. We say, I'd like 1 million photons in the scene, please. It actually fires lights continuously. It goes through each light, and the lights build up like a probability of firing based upon their energy level. So they'll always fire in turn based upon their relative energy. You'll get at least the number you wanted. So because of the nature of this, both the number of lights and the fact that when you do fire the photons, some of them can be stored and reflected. You can end up with more. So if you ask for 1 million, you might end up with 1,020,000, or 1,005,000, 1 million and a few. So you get slightly more than you asked for. Once you do have those though, you actually divide the number of photons that you've got by the energy of the lights. The original 60 watt lights there, estimate of lights coming through window, spotlights over there, whatever, you add up all the incoming light, the direct light, and you divide it by the photons, whatever, you actually correct the photons. So all the photons have the, they don't have the same energy. When they're emitted, they have the same energy, but we adjust the energy in the scene to be conserved and distributed correctly. Okay? When we emit them again, because remember there's two phases here, we render the direct light as a normal direct light, as you would, and we render all the indirect lights as if they were direct. Then they just light using their normal lighting functions, just standard. There's nothing. I said that I did an area-to-area transfer, which is just slightly more complex than like a dot product type lighting with the decay. So no, there isn't a problem with that.
And that way you don't have to deal with calculating that attenuation on every photon. You do it as a post.
Now, because it's using floating point values throughout the whole system, you are right. You've got a big room with dim lights. The light will end up on a wall, and a little bit of that light will reflect across the room and decay and end up over there. But the nature of it was, the whole point was that when we simulated the light, we end up with a tiny, low quality, a very dim light near the surface. Lots of them, dim lights near the surface, and they all added up together to produce a very dim light on that surface, at the surface. Not so that you don't actually broadcast across the scene very much. We're trying to do the final bounce. So we're saying that light came in and it finally ended up there. We emit that final bounce.
That's good. Thanks, Rick.